with it a little bit and decided that we were going to do it as microcoulombs. Now, I'm going to challenge you folks. If you're somebody who wants to beat me to it, because you've seen the recipe now, I'm going to work away at this problem. You can follow with me and you decide, are you going to write with me or are you going to try and race me to the finish line, okay? If you race me to the finish line, please try to use proper notation. That's all I ask, okay? See if you can do it. I'll narrate a little bit as we go. All right, so we got these 2-point charges, Q1 and Q2. Q1 is negative 1.0 microcoulombs. Q2 is also negative, but 3.0 microcoulombs. And just a reminder that a microcoulomb is a millionth of a coulomb, so 10 to the power of negative 6. 1 microcoulomb is 10 to the power of negative 6 coulombs. So we'll have to do that modification, just convert it over to our SI units. I don't really have a good reason for this, but I'm going to call to the right positive and to the left negative, just because I did that once before, and we'll see if that works out for me. It says that these 2 point charges are 0.5 meters apart, and we're investigating what the electric field is at the midpoint. So the electric field is here, and that means that I've got an R2 value equal to 0.25 meters, an R1 value equal to 0.25 meters. And again, sort of symmetrical, but we have charge imbalance. But this one isn't truly a dipole. They're both negative this time. So when I go to investigate what's going to happen with the epsilons, with the electric fields, epsilon 1 orients toward Q1. So at that point, I'm going to have epsilon 1 orienting towards Q1 because the convention is that electric fields orient towards negative charges. Epsilon 2 orients towards Q2, which is also negative. Electric field orients towards it. So those two vectors represent the electric field that's occurring at that test point. And if you want to label it a point P, you can, but the question didn't tell us to. But oftentimes we do label our test points as point P. All right, so we got sort of our physical map drawn out here. Kind of like a free body diagram, but not really. Field orientation diagram. So the total electric field is going to be epsilon 1 plus epsilon 2. And if you like, there are some people that will call this field superposition, because by saying that one charge causes one electric field and the other charge causes the other electric field, but there's no such thing as electric fields crisscrossing at a point, what we're really doing is superimposing those two fields on top of each other to figure out what the net result is going to be, right? So field superposition is a word that some people might use to describe that, because it can't be uphill this way and uphill that way at the same point. So we have to find the net. What's the superimposed electric field going to be? So epsilon 1, and I'm going to leave myself space for positive and negative orientation signs, is KQ1 over R1 squared, absolute values, plus, and again, I'm leaving myself a little bit of space to deal with the reference frame, KQ2 over R2 squared, absolute values. I look at epsilon 1. Epsilon 1 was to the left. To the left was negative on my reference frame. So even though all the charges are negative, I'm now dealing with my reference frame positive negative convention. So that guy is a negative value. This one's to the right, and so it gets to stay positive. If you really feel like throwing in an extra positive sign, you can, but it's a little bit silly, honestly. It's just, if we're just trying to push the point, I suppose. Now you can factor out a k if you want to, but what that's going to mean is that it's k times negative absolute value of Q1 divided by R1 squared plus absolute value of Q2 over R2 squared. And now, because we've done microcoulombs instead of coulombs, which is maybe arguably more realistic in terms of how much charge we'd have at a point, epsilon total is equal to 9.00 times 10 to the power of 9 Newton meters squared per coulomb squared times, there's that negative sign, negative of the absolute value of Q1 is negative 1.0 times 10 to the power of negative 6 coulombs. And if you like, we could put absolute values around it because it used to be negative, but we've dealt with it. 0.25 meters squared plus, don't forget this negative sign is there when we go to do our data entry, plus Q2, which was our negative 3.0 times 10 to the power of negative 6. But look, this negative sign is going to disappear because of the absolute values, divided by 0.25 meters squared. Close that off. And if you know yourself and you know you're going to mess up if you put a negative sign inside the absolute values and you know that you're just like a sloppy copier, turn that to a positive sign right away, just so that you don't mess it up later, okay? Because that positive sign is there due to the absolute values being there. But we plug all of our values in. This is, at this point, all data entry once we've done this level of processing. And my epsilon total ends up being 2.88 times 10 to the power of 5 newtons per coulomb. Now, if I look at the significant figures on this one, and it's positive, I suppose. If I look at the significant figures on this one, there's only 2 sig figs, sadly, so I reduce it down to 2.9 times 10 to the power of 5. And since it's positive, that means it's to the right. And we could do a little therefore statement, get our part marks. Therefore, the electric field is 2.9 times 10 to the power of, times 10 to the power of 5 newtons per coulomb to the right.